Okay, so the previous video described what VO2 max is, and in brief, it is the maximal rate at which you can extract oxygen from your blood. And typically it's associated with exercise. So, what is the maximal, intensity of exercise that you can sustain that relates to it. But physiologically, what it's actually describing, functionally what it means, is how much oxygen you're able to take out of the blood, and that is a product of two things. The rate of oxygen extraction at the tissue level, and also how much oxygen, or rather how much blood you are delivering. So it's cardiac output multiplied by arteriovenous oxygen difference, and that is written as AVO2 difference. That equation that describes that relationship between total body oxygen extraction and the tissue level extraction and cardiac output is known as the Fick equation. So that's what I described in the previous video. So I use that to sort of give a little bit of a springboard for going into lactate threshold. So, well, what is lactate? I did one video where I ranted a lot about it, and I'm not going to go into all that depth and bore you, but very briefly, it is one of the possible products of the process of glycolysis. So glycolysis is a metabolic pathway in which we break down glucose, right? It can come either from free glucose in the muscle or stored glycogen. Those mechanisms can be discussed another time. But effectively, we have glucose. So my beautiful green hexagon here is a glucose molecule. We break it down through a series of reactions called glycolysis, and we produce ATP. Now, we don't just make one. For every one molecule of glucose, we make 2 or 3 molecules of ATP, depending on the original source of the glucose. Again, that's not really a big issue right now, but this is glycolysis, right? And what do? Well, from that, we produce a product, or actually 2 of them, right? So I'm actually going to put 2 times something called pyruvate, or pyruvate. You can say it however you like. I'm going to abbreviate it PYR. So that is one way we can end glycolysis. And some textbooks will say this is the default way. I think that's not necessarily the case, but I'll get into that another time. The point is, as exercise intensity increases, we have an increased rate of production of something called lactate, which I'm going to abbreviate here and put this in a different color. Say we split off, and instead of creating pyruvate, we create this thing called lactate, and I'm going to write it La-. So lactate is an anion, that is, it's a negatively charged ion, and it's another possible product of glycolysis. And actually, to make this a little bit more accurate, what really happens is that there's an interconversion between pyruvate and lactate. There's an enzyme that catalyzes this reaction, and that enzyme has different forms depending on the individual, what organism we're looking at, and adaptations, what kind of muscle. We're not going to talk about that right now. But this is the guy we're concerned about. Why? Well, you may have heard the expression lactic acid before, and what that's referring to more accurately is the production of lactate, which is not the same as lactic acid, but it is produced in conjunction with, at least as far as what ultimately accumulates in the muscle and what is transported into the blood, it presents with something known as a hydrogen ion right here. Okay? Very poorly drawn. Let me redo that little plus sign there. But this is a hydrogen ion. And acid, or an acidic substance, will have a higher concentration of these hydrogen ions, right? So when the pH gets lower, that is, when something becomes more acidic, we say the pH is lower. It refers to a higher concentration of these guys. So during exercise of increasing intensities, we tend to accumulate more and more of this lactate. Now, when I say accumulate, what I mean is this. If you imagine that there are, and I'm going to just keep using the same color, hopefully it won't cause too much confusion, this lactate, to get used, has to go somewhere. Because if it just sits there, it can sort of eventually back up the works. Lactate can inhibit some of the reactions that we need to keep glycolysis running, to keep muscles contracting, to keep producing ATP. And also we have these hydrogen ions that are also accumulating, right? So as lactate builds up, and as these hydrogen ions build up, eventually we can become more and more fatigued. So our muscles have to do something with that. Well, some muscle cells can effectively metabolize lactate. So we bring them here, and I'm going to get another marker here. And let's say this little jelly bean here is a mitochondria, or mitochondrion since it's singular. Well, part of the reason we may produce lactate in the first place is that we can't get pyruvate in here quickly enough. Some lactate can be brought in here, but regardless, eventually we have to do something with this. Many of the cells that actually produce the most lactate will, instead of metabolizing it in the mitochondria, shift it out here to the blood. And I'm just going to write the word blood down here. Okay? So we will send the lactate away to some other tissue to be metabolized. Okay? So if the muscle cell is producing more lactate than it can get rid of, or it's producing lactate more quickly than it can get rid of it, it starts to accumulate in the muscle cell, and that increases the concentration gradient that drives it into the blood, and so we have this spillover effect. Okay? And that is really where we start getting into the realm of being able to talk about something called lactate threshold. So what is lactate threshold? So through the magic of editing, right, and I'm sure that was totally seamless, I've erased this and I've created a graph here. So what we're going to see in terms of a visualization of lactate accumulation or lactate buildup in the blood is this. So what we have on the horizontal axis is just percentage of VO2 max. So again, that is the percentage of whatever that maximal sort of, that maximal intensity is, or at least maximal oxygen consumption. You can absolutely exercise above this. So I haven't numbered this here, but these are just different hash marks, each representing 10% of your VO2 max. My perfectly spaced little hash marks there. So effectively this corresponds to some range of intensities, or a range of speeds if we're running on a treadmill or cycling or something, but a range of intensities at which we could conceivably exercise for some duration. And that's the important thing here, is that lactate threshold is often used in describing potential for endurance performance. And there are nuances there that are probably better fodder for our future discussion. But suffice it to say, we have on the x-axis or the horizontal axis this intensity sort of value. That's what VO2, percentage of your VO2 max would be as a surrogate for that. And then on the vertical axis, we've got concentration of lactate in the blood. So that's what this represents. That's what the brackets are, as a concentration. And the unit is millimoles per liter, or just millimolar. That refers to the concentration. And so we have 2, 4, 6, 8, 10 millimolar, etc. on this vertical axis. So as exercise begins, and we start off at a really low intensity, we would see not a whole lot of rise. Now there will be some variation from person to person as far as what the resting level is, but in many people the resting lactate level is somewhere around 1. So maybe around halfway here. And they just kind of proceed along. There's not a whole lot of accumulation. We are maybe producing a little bit more lactate as we get more intense with the exercise, but the muscles are taking care of it themselves, so it's not spilling over into the blood yet. Eventually, though, we start to hit a range where we start trickling upward, and that is where we start having an increase in the production of lactate such that the muscle is not quite able to dispose of it or reconvert it back into pyruvate or do whatever it needs to do with it as quickly as it's being produced. And so we see some range, and for an untrained person, it might be around 40%, 50%, somewhere around here, where we start seeing this uptick, right? Now you'll notice this is a curve. Let me make it actually horizontal so it's a better representation. But there's a curve here. So this is not some, absolute exact point. Nobody can really agree on the exact point. You're going to see rules written somewhere, but conceptually the basic idea is this. You get somewhere, and for some people it'll be around 2, maybe even 4, somewhere between 2 and 4 millimolar, depending on the resource you're reading and the situation and the person you talk to. But we start seeing a pretty rapid increase in the blood concentration. So the slope of this line starts going up. And a little while later, we may see an even bigger tick, and suddenly we get this exponential rise, like this, in lactate concentration. Now, this initial region where we first start seeing that uptick, we might term that the lactate threshold. So I'm going to put LT right there, pointing to it, my very sloppy slanted T, right? And then we have another thing that people often use interchangeably with lactate threshold, which is OBLA. So I'm going to write that term right here, OBLA, which refers to onset of blood lactate accumulation. Now, definitions for this will vary a little bit depending on, again, what resource you're reading, but often you're going to see this expressed as a slightly different time point or a slightly different point on this graph. For example, if we're halfway between, let's say, the 4th and 5th hash marks, so that would be 45% of the person's VO2 max, right? We would say their lactate threshold occurs around the 45% mark. This is a person who's not necessarily very well trained. They're not about to keel over and die probably, but they're a marathon runner, right? And then some point later, where we see often above 4 millimolar as the concentration, typically above 4, we'll see some other range that might correspond to this OBLA thing, right? Somewhere around here or even a little bit later here, right? The exact point is going to depend on the individual and the circumstances, and again, what person you're talking to. In my experience in the exercise science world, we can't completely agree on these terms, but this is a conceptual discussion to sort of get you started. And again, don't get hung up on the exact numbers because those will indeed vary. The shapes of these slopes will vary from person to person. In fact, to give you an example of that, if you have a more trained individual, so somebody, trying not to make too much noise dropping things on my desk here, a more trained individual, say a marathon runner or some other endurance athlete, a cyclist perhaps, you would have a situation, most likely, where their muscles are better able to dispose of lactate at higher production rates. And so they may be cruising along at some similar kind of concentration here, and these lines will start to diverge because that endurance athlete might keep their lactate levels pretty constant until a much higher level, maybe 70, maybe 80% of VO2 max. And so their threshold might be something more like this, right? So happening later. And that says something pretty important for a person's potential for endurance exercise performance. Why? Because, and anybody who's done a lactate threshold test should be able to tell you this, once that lactate starts accumulating, stuff starts to hurt. Exercise starts becoming more uncomfortable. Suddenly you're not just cruising along at an easy pace. It still may be doable, but more discomfort starts to set in. So if you can prolong this, you can, at least in principle, push back that threshold where exercise starts feeling, a little bit more intense and a little bit more uncomfortable. And keep in mind, these are relative VO2 maxes, or relative outputs, I should say, relative intensities. So as a percentage of VO2 max, you may have this person whose lactate threshold is 20% later, 30% later, but then you got to keep in mind that this more trained person also, in terms of absolute oxygen consumption, has a higher VO2 max. So if you graphed those that way, these lines would actually be much farther apart. If that's confusing, send me a message, ask me in comments, and I can try to explain that better, or I can just do another video or upload some pictures or something and share that. But again, you would see something maybe more like this for the more trained individual, right? So lactate threshold is just where you start to see this uptick of accumulation, if you will, or this increase in the concentration of lactate in the blood, and then some point past that, you may see something that we would term OBLA, or onset of blood lactate accumulation, right? Which might be these higher ranges here. They vary depending on the situation, on the person. So I know that got a little messy, got a little bit busy, and the video ran long, but hopefully that gets you started in understanding some of the basic concepts behind lactate threshold. And again, this will vary in terms of the particulars and how you might look at it. Can you train it? Can you change these levels? So you're a little bit more ready for that discussion now, hopefully.